Exercises 5.2.5. So this is section 5.2. And we went over these in class, some of them for questions, but I'm going to go through them all so that you have answers to them all. Okay. So it says, what is g of 0? We have this graph. It's supposed to be f of t. So this is a picture of f of t. And g is the area under f of t from 0 to x. So what is g of 0? Well, if we go from 0 to 0, the area under the graph is going to be 0. So g of 0 has to be 0. And what is g of 1? Well, I'm going to bring up the larger graph. 1 is here. And if this is f of t, and g is the area under f of t from 0 to x, and we want g of 1, we want g prime of 1. So g prime would be the derivative of this. So g prime of x would be the derivative with respect to x of the integral from 0 to x of f of t dt. So if it's the derivative, and it's the derivative of the integral, this turns out to be just f of x. So it'll be just whatever the value at 1 is. So if we look at 1, the value looks like it's about minus 1.6. Okay? That's the derivative. Now, the interval with endpoints given to the nearest point 0.25, where g is concave up, okay? So this would be a picture of g prime then. F of t is also a picture of g prime of x. And g prime, so the where g is concave up. So that means the slope of the derivative has to be positive to be concaved up, and so it looks like it's concaved up from about 1.25 to 1, 2, 3, 4, 5, 6. So looks like on the interval 1.25 to 6. So they say give it in an interval notation like this. The value of x where g takes its maximum on the interval from 0 to 8. When is it maximum for 0 through 8? When is g, what x value is g the maximum? Well, g is the area under the curve as we go out. And if g of 0 was 0, and we go down that much, then we go up all this area. The area under here tells us to go up. So we went down, and then we're going up, and we're still going up, and so at 8, we have the maximum area. Number 2, so we have the derivative of x to a. Now normally if it was a to x, and the derivative of the integral, we could just put x in for the t. But these are backwards, so it would be just negative ln of x And that would be it. Approximating the function with a derivative. So this is the derivative of some function. So they're saying right here, this is the derivative, and f of 3 is 0. So at f of 0 is 3, 1, 2, 3. And if the derivative looks like this, the area under the derivative tells us how much this changes. So we need to find the area under this derivative from 0 to 4 to be able to figure out f of 4. So we're going to pull out our calculator and type in that equation. So e to the negative x squared over 5. So I have it typed in already. I'm going to retype that x so that I can say graph, and it'll regraph it. And now, if we can figure out the area between 0 and 4, we can add it to the 3 and get the height of f of 4. So let's see, let's get that out of the glare. There we go. So I want to find the area under this curve so I can calculate the area from 0 to 4. And it gives me 1.95905-ish. So I add 4 to that, and I would get, I add 3 to that, I get 4.95905 approximately. Now, if you just drew a graph of this and then estimated the area, which would have been about 1.5, if you figure, or about 2, you go across and down for 4, go up to 1 and go over 4. That rectangle would have an area of 4. This looks like about half of that. So we'd say 2 added to 3 would be 5, and we'd be pretty close. And that would be another approximate, but it's not close enough for what they have in the book. Number 4. So this is a picture of g of t. That's what's inside. And f is a function of the area under g of t. So this starts at 2. F of 2, from 2 to 2, would have to be 0. So over here we're supposed to graph f of x. And at 2 it has to be 0. Now, 2 is right here. So we need to know the area in here to know how this will go on. Well, they say area 2 is 12.75, and that the area of 2 that's between 0.5 and 2, this area, is 6.06. So 6.06 plus 6.69 would give us the total area of this, which means when we go 2 to 4, we're going to go up 6.69. So if this is 5, that's 7.5. So 6 is probably about there, and 8's about there. 6.69 is really close to 6.5. It's getting about that high, so that's where it is at 2. Then it goes down area 3, which is 3.36, so 6.69 minus 0.36 is 6.36. 6.33. That's getting closer to 6, which is not much lower. And that happens at, let's see, at 2, I got to get over to 4, it's this height. So there's 4, that's where it's that height. The 6.69, so it's 4, 6.69. And then at 5, it goes down to 6.63, so the next point is 5, 6.63, which is very slightly down. Forget that point. And then at 6.5, we add area 4. Area 4 is 1.79. 1.79 added to that, that would be a 2, carry the 1, that'd be 1, carry the 1. 8.12. 8 was about this high. 8.12 would be slightly higher. So there is 6.5. 8.12, that would be this point. Now let's go back. Okay, so we were adding area, so this graph was going up when it got to 0 at 2, so we have to go down 6.6, 6.06, so 5, 6, 7.5, 7, 6, so right about here, 6.06, at 1/2 is about where it is there. So this point is 0.5, comma, negative 6.06. And back here at negative 1, area 1 was 4.29. 4.29. Now that's negative area, which means the function was going down and got to this minus 6.06. And so we have to go up. So from the negative 6.06, we have to subtract the 4.29. 6.06 minus 4.29, and our answer will be negative, although this would be positive, but we're going to be still negative because we're more negative. If this is negative and this is positive, we're going to subtract. We're going to get negative 7 and 9 and 1.97. So that's 2.5. So there's 2, there's 1. 1.97 is roughly 2, and that's at negative 1. So negative 1, it's negative 1.97. Now, so we have a graph that kind of goes down and does this. Let's just check curvature here. So negative slope, so this has to be curved down. Slope is 0, so this is a max here. Curve down, concave down, and slope is 0 at that place. So that's a max. This is a max. And then here at 1/2, the slope is positive. The slope of this graph is positive, meaning this is concaved up, and the slope is 0 right here of this graph, with a positive slope on here, meaning concaving up. So this goes down and concaves up. And then it goes to 2, and 2, it's concaved up all the way until it reaches a steepest part, so it's concaved up. And then at 4, it's reached a max. The height is 0, and it's a negative slope, so it's concave down. So that's a max. And then here the slope is again 0, but it's positive slope, so it's concaved up. So this has to be a min. And it goes like this. So this is a min. This is a relative max. And this is a relative min. and this is the relative max. Okay, so we've discussed where f is 0, where it's increasing, where it's decreasing, concaved up and concave down. Gone through all the pieces. 5. The tide removes sand from the beach at this rate. So the question I asked in class, is it always removing sand? And a sine curve, no matter what this is here, the sine can go from -1 to 1. So we could have 2 minus 5, or we could have 2 plus 5 at the extremes. Well, 2 minus 5 is -3. And if this is the removal of sand, and -3 would be negative removal, which means the tide will sometimes be adding sand, and when it's a 1, this would be 7, it would be subtracting sand, removing sand at a rate of 7 cubic yards per hour. So, again, this will be always removing sand, the rate of removal, and then it says they have a pumping station that adds sand. And the reason they're doing that is because they want to make this a nice beach and they want it to be sandy, so it would be adding sand, and this is what the tide is doing. Sometimes adding sand, but most of the time subtracting sand because of the +2. So, write a definite integral that measures how much sand the tide will remove during this time period. Okay, from 0 to 6. So that would be the integral of r of t from 0 to 6 of, we could just say r of t dt, but we can say 2 plus 5 sine 4 pi t over 25 dt. So that's the sand being removed. Write an expression for y of t, which is the total number of cubic yards of sand on the beach at time x. Okay, so we would have, explain your reasoning. Now the beach holds 2,500 cubic yards of sand at time 0. So y of t would be, it had 2,500, and then it's going to get added the sand from the pumping, which would be the integral from 0 to x of the area under this curve, 15t over 1 plus 3t dt. That would be the sand added to the beach. And then this is the sand removed, so it's going to be minus. Oh, and we want to take this would be the sand added, yes. Cubic yards. This is how much there is, and then the area under the change curve tells us how much is being added, and then the area under this change curve is how much is being subtracted. Minus how much is being subtracted, so we'd go from 0 to x of the 2 plus 5 sine of this 4 pi t over 25 dt. So this is how much sand would be. What's on there normally plus the area in the curve tells how much the change is, and this would be adding, and then this would be subtracting from 0 to x. At what instantaneous rate of change is the total number of cubic yards on the sand at the beach at 4 seconds? at 4 hours, 4 hours, what's the instantaneous rate of change? Well, that would be the derivative of this, which means we would we'd take the derivative of this, and the derivative of the 2500 would be 0. The derivative of this would be just x in place of that. So it would be, and we're doing it at time 4, so it'd be 15 times 4 over 1 plus 3 times 4. That's how much sand would be adding at that time, the rate of change of, or the rate of adding sand, and then the rate of subtracting sand to get the rate overall. We would put in the x into this and then replace it with 4. So we'd have minus 2 plus 5 sine of 4 pi times 4 over 25. And that would be the instantaneous rate of change of sand, figuring out whatever that is. And over the time interval of 0, 6, at what time t is the amount of sand on the beach the least? So we'd want the minimum value of this from 0 to 6. So we would take the derivative, which would be this minus this, and graph that, and when it's 0, we will have a minimum value or a maximum value. So let's put those into the calculator here and see if we can get those answers. So we'd have 15 tx divided by 1 plus 3x minus 2 minus 5 sine of 4 pi x over 25, close parenthesis, and let's go, this is 0 to 6 seconds, so let's go zoom forward, we can see what's going on here. Yeah, it might be too close. Okay, so there's a 0 at just a little bit past there. Let's find that 0. So I can calculate the 0 between, oh, let's see, 1, 2, 3, 4, 5, and 6. Between 4 and 6. 4, enter, 6, enter, and it says, oh, guess, about 5, and it says 5.11 hours. And is this a max or going to be a max or min? Well, this has got a positive slope on this derivative, which means it's concaved up, which means it's representing a minimum. So at 5.11 hours, we have a minimum amount of sand. Okay. And now the last one, an aircraft problem that we talked about earlier. So it's going so many feet per minute, and as the air gets thinner, it gets harder to climb at that rate of climbing, and then it says give a function for the minutes, and so m, which is a function of the h, will be in minutes per foot, and that would just be the reciprocal of this, so 1 over 925, 1 over 875, 1 over 830, etc., etc., etc. So there's the table for that. I didn't complete it, but that's the idea. Give a careful interpretation of the function whose derivative is m of h. So if m of h is how many minutes per foot, then if it's the derivative, then the antiderivative would be the cumulative minutes, the total minutes to climb to those heights. That's what the careful interpretation would be. Determine the definite integral whose value tells us exactly the number of minutes for the plane to ascend to 10,000 feet. That would be the integral of m of h dh evaluated from the heights of 0 to 10,000 feet. And clearly, explain why the value of this integral has the required meaning. Because if we find this is the rate of change in the minutes, and the area under the change tells us the total change. So this would be the total minutes changed to get to 10,000 feet. Determine a formula for the function f of h whose value tells you the exact number of minutes required for an airplane to ascend to h feet. Now, I don't like that they said h. It would be nice if they said to x feet, so that we can find this equation. M of x would be the integral from 0 to x of m of h. The area under the m of h curve evaluated up to x for the x number of feet. But if they want us to put h here, then I'd have to put a different variable here, x here and here. Now it says estimate the values of capital M of 6,000 feet and 10,000 feet as accurately as you can. Well, I'm going to be roughly accurate. For 6,000 feet, that would be from here to here. I need to find the area under this curve. So I can do left-hand integrals, 1,000 wide, and use the left-hand value, which should be this one. 1,000 times this, 1,000 times this, 1,000 times this, 1,000 times that one, 1,000 times this one, and 1 over that, and 1,000 times 1 over that. That would be left-hand. Or I could do right-hand, this over that, and 1,000 times that, and 1,000 times this, and I could do that. But I think I'll do midpoint. It would be less calculations, and midpoint comes out pretty close. So I will divide this into 3 sections and do the midpoint of this is 1 over 875 times 2,000 plus width is 2,000 times 780 times 1 over 780, excuse me, plus 2,000 times 1 over 685. And for 10,000, I'd have to do 2 more intervals. I'd add to this 2,000 times 1 over 585 and 1 over 2,000 times 1 over 490. And that would be the amount of minutes to get to 10,000 feet. And those should be pretty close if we're doing midpoint. And that may have been off your screen, so I'm going to leave it there for a sec so you can see that.